Hello everyone, this is Mr. Tanner, and today for our notes we will be looking at atoms and molecules. We will also be looking at how atoms are arranged on the periodic table and some of the most important molecules that we have for life. Also, those happen to be some of our more common molecules on Earth. So without any further delay, let's get started. We'll start by looking at the definitions of atoms and elements. So an atom is the basic building block of all matter. So anything that we know of in the universe that has matter or has mass is made of 118 known atoms. And atoms are all built from different combinations of protons, neutrons, and electrons. So again, atoms are the basic building blocks of all matter on Earth, and matter is anything with mass. And all atoms are built up of protons, neutrons, and electrons, and different atoms would have different numbers of protons, neutrons, and electrons. An element is any substance that consists of a single type of atom. So elements can be made of hundreds of trillions of atoms or more easily, but they all only have one type of atom. So an example of an element would be oxygen gas. It's just O2. It's filled with oxygen. Or if you had a pure gold bar, there would only be gold atoms inside that element. So an atom is a single atom. Elements can have huge numbers of atoms as long as they are all the exact same type of atom. So that means to be the same type of atom, they all need the same number of protons. The protons are what determine what type of atom we have. Before we can dive into the periodic table and understand how all of the 118 known elements are organized, we need to start by looking at a single piece of the periodic table, which is an element square, because the element square gives us a lot of information about the composition of an atom. So here on this page, we have the element square for sodium, and this will tell us the number of protons, neutrons, and electrons that exist within sodium. But in order to know that information, you have to know the properties of the different subatomic particles, which are protons, neutrons, and electrons. So make sure you draw this little table that I've drawn to the right of the element square that has the subatomic particle, it has the mass, the charge, and the location of a proton, neutron, and an electron. So we'll start with a proton. Protons has a mass of 1. So it's just one atomic mass unit is a proton. Its charge is +1. And those charges can add. So if an element has one proton, it has one positive charge. If it has two protons, it has two positive charges, so it's +2. 3 protons gives it a +3 charge. And finally, its location is the nucleus, which is the very center of an atom. If we were going to draw, for example, hydrogen, the simplest atom, it has one proton in the center, and it has the nucleus, that is, and then it has one electron that would orbit. This dotted line is the orbit. The bigger dot here is the electron. So it has one electron that orbits the nucleus. But protons are found in the nucleus. So again, this would be for hydrogen. The next subatomic particle is a neutron. It also has a mass of 1, but it has no charge at all. You can add as many neutrons as you want, and it will never impact the charge of that atom. And just like the proton, the neutron is found in the nucleus. So if we bumped up to the next element, which is helium, so we'll turn this hydrogen into helium. Helium has 2 protons. Oops. Helium has 2 protons, 2 neutrons, both in the nucleus, and then we would add a second electron orbiting the nucleus. So now we've made helium. And for the last subatomic particle, electrons, they have a mass of 0. It's not actually 0, but it is so tiny compared to the mass of a proton and neutron that we can add hundreds of electrons and it doesn't impact the mass of the atom in any significant way. So we just round it down to a mass of 0. And electrons have a charge of -1. So the charge of a proton and the charge of an electron will cancel each other out to create an atom that has no overall charge. An atom that has a charge is called an ion, and we'll get to that. So that would be an ion if it had charges. The location of electron is, I'll have to write this small, orbiting the nucleus. So electrons are not in the nucleus, they orbit the nucleus. So now that you have the information, the characteristics of these subatomic particles, we can use this element square to figure out all of the information within an atom. So having gone over the subatomic particle properties of protons, neutrons, and electrons, we can now use this element square to understand how many of each of those things any atom has on that square. So if we break down what's in an element square, we have the element name. In this case, it is sodium. We have the element symbol. We have the atomic number. And we have the atomic mass. The element name and element symbol are pretty self-explanatory. They just are the name and the symbol we use to abbreviate that name on the periodic table. The atomic mass tells us the number of protons. Tells us the number of protons. So the atomic number of sodium is 11. Sodium has 11 protons. The other nice thing about the atomic number is because all elements on the periodic table have a neutral charge. They have a charge of 0. But 11 protons gives us 11 positive charges. So to cancel out each of those positive charges, we would need a negative charge. So this also then tells us the number of electrons. So it's also the number of electrons. Now, not all atoms are always neutrally charged. They can form ions, which means they have either a positive charge or a negative charge. And if that's the case, there's an easy equation to calculate the number of electrons. So you can just say number of electrons equals number of protons minus the charge of that element, or of that ion, I should say now, if it's charged. So sodium frequently forms a +1 charge. It really likes to lose one of its electrons, and it forms a +1 charge. So in that case, we would have 11 protons minus the charge of +1, and 11 minus 1 equals 10. So very frequently, sodium has 10 electrons when it has a positive 1 charge. This would never happen, but let's pretend that somehow sodium had a negative 1 charge. Then it would have 11 protons, and you would subtract a negative 1 charge. Well, 11 minus a negative 1 equals 12. So that would tell us that we would have 12 electrons. So if there's no charge, the number of electrons equals the number of protons. But if there is a charge, then it's the number of electrons equals number of protons minus the charge of that atom. So the atomic number, again, tells us protons and electrons because we know the charge of the atom. Atomic mass, on the other hand, equals the number of protons plus the number of, not electrons, of neutrons. And this is really important because we already know the number of protons, so this is a known in this equation. So for sodium, we know there is 11 protons, and we know the atomic mass is 23. This 22.99, we just round that to the nearest whole number, which is 23. So this equation tells us that 23 equals 11 plus however many neutrons we have. Well, we just rework this equation, subtract 11 from each side of the equation. 11 minus 11 is 0, so those cancel out. And 23 minus 11 is 12. So this diagram tells us that sodium has 12 neutrons. And again, that comes from this equation, atomic mass equals number of protons plus number of neutrons. I know there's been a lot of information on this slide, but it's an important concept. You have to get to the point where you can look at this element square and in a relatively short period of time, tell me how many protons, how many electrons, and how many neutrons that element has. So this is going to be a really important video. You can re-reference this anytime you forget what we're looking at, but make sure you have these equations written down because you should be able to tell me for any element square the number of protons, neutrons, and electrons. Now that we've dived into that, we can actually look at the periodic table. And we were just looking at sodium, which is located here on the periodic table. But the periodic table is organized mainly by the number of protons. So if you read this like a book, reading from left to right and then top to bottom, we would have hydrogen with 1 proton, helium with 2 protons, lithium has 3, beryllium has 4, boron has 5, 6, 7 for nitrogen, 8 for oxygen. So we're just counting up by the number of protons. But that doesn't explain why there's gaps. Like, why is there such a big gap between hydrogen and helium? Why is there such a big gap between beryllium and boron? And that's what we're going to talk about here. So rows on a periodic table are oriented left to right. So you can see there's a row here. That's one row. This is a row. This is a row. And if you look, we have 1, 2, 3, 4, 5, 6, 7 rows on the periodic table. These are not separate rows down here. We'll talk about that in just a second. So 7 rows on the periodic table. There's a lot more columns. Columns read top to bottom, but there's really only 8 columns we need to pay attention to. So we have column 1, column 2, column 3, 4, 5, 6, 7, 8. And again, we have row 1, 2, 3, 4, 5, 6, 7. So columns and rows are how we're organized. The rows just count up by protons. So they count up by protons. The columns group by similar characteristics. So we can say that column 1, lithium, sodium, potassium, rubidium, cesium, and francium all have similar characteristics. They're all in the same column. And the reason why they have these similar characteristics is due to the electrons that they have in their outermost shell. And we'll look at that as a class a little bit later. Column 2, beryllium, magnesium, calcium, strontium, these all have similar characteristics. Same with column 3, starting with boron, aluminum, gallium, those all have similar characteristics. Column 4 has similar characteristics. Column 7, all of these columns, whether you go down, every atom in that column has similar characteristics to one another. The different columns, however, have very different characteristics from one another. For example, column 8 are the noble gases. They don't react. They don't react with hardly anything because their outermost electron shell is full. Column 7 is only missing one electron from a full outer electron shell. And what's kind of neat about that is that column 1 only has one electron in their outermost shell. So elements from column 1 really like to form bonds with elements from column 7. And for example, sodium readily bonds with chlorine to make table salt. That's sodium chloride. So based on the column properties, we can kind of predict what elements are likely to form bonds and their characteristics. So that's reading a periodic table. Going across the rows is just counting up by protons. Columns group elements into their similar characteristics. And you'll have an assignment that dives further into that as well. And finally, we're going to talk about the definition for molecules and then look at some common molecules on Earth, especially molecules involved in life. So molecule is a substance that is made up of multiple, or a better way would just be two or more types of atoms bonded together by their electrons. The electrons are what bond things together. And there's two major types of bonds. There's way more than just these two, but the two strongest bonds that can form are ionic bonds and covalent bonds. Ionic bonds form when one atom donates electrons to another atom. So it actually creates an ion where one atom is positively charged and one atom is negatively charged. And since opposite charges attract, that positive charge is really strongly linked to the negative charge on the other atom. Ionic bonds are the strongest type of bond that forms. The next strongest is a covalent bond, and this forms when atoms share their electrons. So the electron would orbit one atom and then orbit the other atom, and it just moves back and forth, and they're shared between two atoms, which is a really strong bond, but not quite as strong as an ionic bond. So again, there's ionic bonds that donate electrons to another atom. Covalent bonds share electrons. And I always remember this because the prefix co is often doing with working together, right? You cooperate with someone else. So you're working together. A covalent bond, the atoms work together by sharing their electrons. And then very last slide here, let's look at some common everyday molecules. Like I said, table salt is when sodium ionically bonds with chlorine. So what we end up with is sodium has a positive charge, chlorine has a negative charge, and then those two charges stick together. And they actually form these little, like we call them lattices or crystalline structures. So they just alternate. We'd have a sodium, chlorine. And then below the sodium, we'd have another chlorine. Here would be a sodium, chlorine, sodium. And they just form these square cubed structures of alternating sodiums and chlorines. Salt's also important because when you put it in water, those ions all break apart and we get lots of charged particles in the water, which is useful for a lot of chemical reactions. Water is when hydrogen, two hydrogens specifically, are bonded to an oxygen molecule. So we have water is H2O, there's two hydrogen, and they're each bonded to an oxygen molecule. I'm going to skip, actually we can go to proteins next. So proteins are made of a structure called amino acids, and there's 20 of them. There's 20 different amino acids that can all link together. And each amino acid is different, but they have something in common. So every single amino acid has a structure that is a carbon, and that carbon's bonded to a hydrogen. And then on one side of the carbon, we have a nitrogen atom and two hydrogens bonded to that nitrogen. And this would be a good time to mention, you don't need to write these down or memorize them. I'm just showing you some common molecules. So this is what's called the amino group. This is where we get the amino acids from, this nitrogen bonded to the hydrogens over here. And then to the other side of the carbon, we have is called a carboxyl group. It's carbon double bonded to an oxygen. That's just a stronger bond. And then over here we have oxygen that's bonded to a hydrogen. And then there's one last bond on this carbon that we just call an R group. That doesn't stand for an element. There's not an element R. This is where the 20 different amino acids differ from one another. There's a lot of different things that can then chain off from this central carbon, and each one of those is a unique amino acid. Finally, we have sugar, which has 6 carbons, 12 hydrogens, and 6 oxygens. They're actually kind of cool because the carbons form a chain. So you go like carbon is bonded to an oxygen here, bonded to a carbon, bonded to a carbon, bonded to a carbon, and they actually make these hexagon structures within sugar, which is kind of fun, but you don't need to know that. And then fats have different structures again that bond to them, but essentially they're just really long chains of carbon bonded to one another, and then they have hydrogen bonded to the other sides of the carbon. And it's called a hydrocarbon chain, hydro for hydrogen, carbon for the carbon. And then they have different things that these hydrocarbon chains can attach to, like a glycerol or something like that, but that's what fats are. And if you've noticed, I've chosen these because these are the 3, like proteins, sugars, and fats are the 3 macronutrients involved in all animal consumption. We have proteins, sugars, and fats, and they're pretty common molecules on Earth. So I know this was a long set of notes. You don't need to write every single thing down. Hopefully that note sheet was helpful to you, but there's a lot of information around elements, and it's important to know. So as always, thanks for watching.